Okay, so for the first part we left off, I had just shown you, hopefully, the mind-blowing fact of where these equations come from. Now, you might be thinking, well, there was a third equation, right? I saw VOTAT, and then I saw my delta x equals v sub 0 t. I've seen those, but the third equation, which, by the way, you do actually have on your equation sheet still, the v squared equals v sub 0 squared plus 2a delta x. Right, so you still always have this to work with, and by the way, you will have these all to work with. So while the derivations are pretty cool, and I hope that makes sense where they come from, you certainly don't need to be able to reproduce this necessarily for this course. And I'll let you know if there's any chance you need to do that for a quiz or test. But probably not. Probably just helpful to see where it comes from. But what about this third equation? Well, I'm not going to work all the way through it, but it is actually still pretty interesting to see. This third equation comes from if I take my delta x equals v0t plus 1/2 at squared. So if I start with this relationship, and then if I know that the acceleration equals delta v over t, and if I in fact break the delta v up into v final minus v initial over t, if I solve this relationship for t, so if I solve this for t, it would be v final minus v sub 0 over a, right? So I would take this, just rearrange it a little bit, and solve to get v final minus the initial over a. If I then substitute this whole value into my position up here, everywhere that there is a t, and then if I do just some kind of fancy algebra, if you will, and you could probably see that before too long, but if I plug that in and just clean it up, eventually I get down to this equation. Okay, so if you're interested in that, you can certainly try it. The algebra does get a little bit hairy at some point because you do have to try to make sure you're getting a common denominator, and then really at some point you're looking for a difference of squares, which helps you out. But anyway, I'm not going to work all the way through the algebra. If you're interested in it, let me know, but I won't waste your time with that here unless you particularly want to see it. But it's still cool to see that this comes from somewhere, right? It's not like they just made that up. It does, in fact, have its origins through the others. Okay, so then at the bottom of your example page for this stuff, you do have a graphical summary. And really the important thing I want you to be comfortable with here is it's very likely that you will have questions on tests. So if you're planning on taking the AP, which I hope you are, and even just the tests that you'll take for me if you're willing. But anyway, you'll have questions that ask you, if the position is a straight line, what does that tell me about the acceleration? So as an example, if we're looking at, right, if we know that the position is a straight line, then wouldn't that tell us that in some way, shape, or form the function would be maybe just an mt to the first power plus or minus whatever, right? So plus or minus a, if we want to call a, or whatever variable. But in this case, if we knew it was a straight line, it would be just a power of 1, right? So we would know that the derivative would be a horizontal line because it would have a slope of 0. And the acceleration would be 0 because its velocity is constant, right? So there is no change in velocity, and therefore the acceleration would be 0. Okay, so I do expect you to be pretty comfortable with translating to and from, and vice versa, right? If I told you the acceleration graph was 0, what does that mean for the velocity? Well, it means the velocity better be a horizontal line, right? Because my slope of the horizontal line better be 0, right? So the slope of my velocity better be 0. And then similarly, if I tell you the acceleration is 0, well, we know the constant velocity, and so that better mean that I have a constant slope for my position. Okay, so there's a lot that relates between these graphs, and I do want you to be comfortable with those relationships. Working on this next one over here, if I told you that the acceleration was constant but not 0, and you'll see it, I think there's even a homework question that asks about this. So if the acceleration is a non-zero constant, what does that tell us about the velocity and eventually about the position? Well, if it's a non-zero constant, then we know that there is a change in velocity, but the slope of my velocity would be constant as well because that acceleration is constant, right? So I know that the velocity would be a straight line, and so if the velocity is a straight line, again, what that tells me is it's some function that looks something more or less like this. Well, from going from the velocity to the position, right, mathematically we would integrate that. So what would that tell us about the position? Well, that would tell me that the position, if the velocity has a t to the first power, the position would have to have something. It wouldn't be m anymore, it would be some new constant out front. but it would have something to the second power, right? And then plus or minus maybe something to the first power. Okay, so the fact that the velocity is a straight line tells me that the position better be a parabola, better have a quadratic shape. Okay, so there's a lot of information. Hopefully this seems simple, but it's very powerful as well. By looking at the nature of the acceleration, you should be able to tell what the position function should roughly be doing. Okay, so if the acceleration was a straight line, think about that. So if the acceleration was a line with a slope, think about what that would tell us for the velocity, and think about what that would tell us for the position function. Okay, so obviously feel free to pause this if you'd like, but I want you to think about that, and then obviously if you have any questions, come find me, and I'll help clarify that. But very powerful stuff, even though hopefully it seems pretty simple. Okay, so with the rest of these examples, we're really just going to get back into what we used to do. There are one or two of these examples that will use some calculus, but for the most part, these examples are just going to get back into what we did last year, except the calculations will get a little bit trickier, because as you've seen in the homework, we will do a lot more work where we have to do systems of equations this year. Okay, so we'll have a lot more examples where we actually have to do some systems of equations to solve them. Okay, so in the remainder of this part and then the next part as needed, we'll see some of those more difficult examples, and hopefully you feel pretty comfortable then with the homework. But let's start with this one. This one actually should be one that hopefully right from the get-go you guys all feel comfortable with. Right? We've got a rocket sled. It accelerates for 50 meters per second for 5 seconds, then it coasts for 3 seconds, then it deploys a braking parachute and accelerates at negative 3.0 meters per second meters per second squared until coming to a halt. What is the maximum velocity of the sled, and what is the total distance traveled? Okay, so two parts of this, but really if we go back to last year, this is just the type of question we have to break up into 3 different stages. We know there's one stage where it's accelerating, right? We've got that information. There's a second stage where it's moving at some constant velocity, but wouldn't this constant velocity just be whatever the final velocity reached from that first stage is? And then finally the stage where it's decelerating, where it's slowing down, right? It's accelerating in the opposite direction until it comes to a rest. So we really just have three different stages, and we can work with those pretty much independently because they give us enough information. So for part A, what is the maximum velocity? Well, when is it going to reach its maximum velocity? That's going to happen at the end of its acceleration phase, right? So really, for part A, all I need to do is look at that first phase of motion, right? For the first phase of motion, for phase 1, if you will, I know, and it doesn't actually tell me, I should have said in this example that it starts at rest, but we will assume that it's starting at rest unless they tell us otherwise. We know the acceleration is 50 meters per second squared, and we know that it's doing so for 5 seconds. Okay, so we've got these pieces of information. So if I ask you to find the final velocity, well, the final velocity is just v sub 0 plus a delta t, right? A times t. So easy enough to calculate. I know my initial velocity is 0, I know my acceleration is 50, I know my time is 5. So the final velocity it reaches, obviously a very, very quick velocity here, but 250 meters per second. Okay, so that's actually then my answer for part A. So that part hopefully was very easy. Part B, it does get a little bit trickier. It asks us what is the total distance traveled, but in order to find the total distance, right, I'm just going to find the displacement for the first phase of motion plus the displacement for the second phase of motion where it's moving at a constant plus the displacement it goes while it's slowing down. So I'm truly just going to break this up into 3 different stages and find each displacement. So I might as well, since I've got all of the information for this first phase, I might as well find that first displacement, right? So at this point, since I know the other 4 variables, you could do whichever equation you want. I'm going to go ahead and just jump in though with the v0t plus 1/2 at squared. Right? I'm going to jump in with this one. So I'm looking for my displacement. I know the initial velocity was still 0, so that's gone. 1/2 the acceleration of 50 times the time squared, so 5 seconds squared. So I end up with half of 50, 25, times 5 squared, so another 25. So I end up with 625 meters for the first phase of motion. Okay, so that's how far we went while it was accelerating. Now you do have to be careful that you don't get too excited by getting this answer correct, right, because we still do have a couple more parts to complete. But that's at least the first one out of the way. For the second phase of motion, right, for phase 2, if you will, we know that the sled, is moving at a constant velocity. And that velocity, right, so it's moving at a constant, and that velocity would equal whatever the final velocity was from this part before. So I know that the constant velocity is 250 meters per second. And what's the only equation we ever use for a constant velocity, right? That stays the same whether we're doing calculus, whether we're doing last year's stuff. The only equation I ever use for a constant or an average velocity is delta x over t. So in this case, I know it coasted for 3 seconds. So it traveled for 3 seconds, it was moving at 250 meters per second, so 250 equals delta x2 over 3. And then solving for that second displacement, I get 750 meters. Okay, so the first 2 stages here hopefully weren't too bad, right? The first 2 stages weren't too bad. So then finding the third, right? I've got to find the third stage of motion. So I know in this particular case that for phase 3, right, it starts to slow down. The initial velocity would be the velocity that we were just moving at, right? So the initial velocity for stage 3 would be 250 meters per second. I do not know how long in terms of time it's going, but I do know that it has an acceleration of negative 3.0 meters per second squared, and it eventually comes to a halt. So I do know the acceleration is negative 3.0, and I know the final velocity is 0. So if I want to find delta x, well, this is a prime example of where I would just go back with my squared relationship, right? V final squared equals v sub 0 squared plus 2a delta x. The final is 0. The initial is 250 squared. Obviously, it is important that we keep the acceleration as negative since we've got it arranged this way. So 2 times negative 3, and then solving for delta x. Okay, so I did that earlier. Allow me to find it real quick. So when I solved for that, and you guys obviously, hopefully will get the same thing, but 10,416 is what I got. So 10,416.7 actually, if I'm being specific, but that's how many meters it went in that third and final stage. So obviously, this car was moving ridiculously fast, and it was not decelerating at a very high rate. So it goes quite a distance during that deceleration phase. So then finding my total distance, it's just 625, right? So finding the total displacement for part B, which is what it asked us to do. So 625 plus 750 plus 10,416.7. Okay, so I've got these measurements, I simply add them up, and Kenny says the answer is 11,791.7 meters. I would tell Kenny that he probably should round this off to 3 sig figs or even 2 sig figs based on the problem, but whatever, it's Kenny, we'll let him do what he wants to do. Okay, so my final answer looks something more or less like that. But anyway, hopefully this example wasn't too bad. It was definitely a lot of review stuff, making sure you're comfortable with the equations. I think you guys are, but I want to make sure you have access to that as well, should you need it. I will not have time to finish this example, so I'm going to go ahead and stop this part here, and then I will pick up these next couple examples in the third and hopefully final part of these notes.